chapter of coordination compounds. Firstly, let me teach you the basic introduction of coordination compounds. Consider the D block elements like iron, copper, zinc, etc. These all are metals. We know that metals love to lose electrons, but here the case is opposite. I mean, these metal elements love to accept a pair of electrons. This iron loves to accept a pair of electrons, this copper loves to accept a pair of electrons, and this zinc loves to accept a pair of electrons. Here, if you ask me why these metals love to accept a pair of electrons, I would say it is due to two reasons. Firstly, these metals have empty shell. Secondly, they complete their octet rule to get stability. That's why they love to accept a pair of electrons. So these metals accept a pair of electrons. Now let me teach you that how metals accept a pair of electrons. Well, consider a metal atom like copper and a neutral molecule like NH3. This metal atom of copper has empty shell. I mean, copper can easily accommodate to upcoming electrons. On the other hand, there is one lone pair of electrons present on nitrogen. So NH3 will donate this lone pair of electrons to copper, and copper will accept this one pair of electrons. Hence, coordinate bond is formed between NH3 and copper. We call this compound as coordinate compound because there exists coordination bond between them. Therefore, we define coordination compounds as the complex compound in which metal atom is bonded to a number of ions or a molecule is called coordination compound. Let me repeat it. The complex compound in which metal atom is bonded to a number of ions or a molecule is called coordination compound. Remember that this NH3 donate a pair of electrons to a metal atom. We call it ligand. So we define ligand as any ion or molecule attached to a central metal atom by donating a pair of electron is called ligand. Thus remember that any coordination compound is made up of two parts. One part is a metal atom like copper and the second part is a ligand like NH3. Thus noted down all these important points. Now let me teach you some basic terms of coordination compounds. Let's consider this coordination compound. There are three species in this coordination compound: chromium, NH3 and chlorine. Now listen carefully. This metal atom of chromium is known as central atom. We know that NH3 donate a pair of electrons, so it is a ligand. This 6 means 6 molecules of NH3. One molecule of NH3 donate one pair of electrons. 6 molecules of NH3 donate 6 pair of electrons. We call this 6 as coordination number. Remember that coordination number shows the number of pair of electrons donated. This chromium, NH3 and the square bracket is called coordination sphere or coordination entity. This chlorine outside the bracket is called counter ion. Secondly, consider this complex compound. Here, cobalt is a metal atom and we call it central atom. This chlorine is ligand. This 2 is the coordination number of chlorine. This NH3 is another ligand and this 4 is its coordination number. This whole thing in the square bracket is known as coordination sphere or coordination entity. This chlorine outside the square bracket or coordination sphere is called counter ion. Thus noted down all these basic terms of coordination compounds. Now let me teach you Warner's theory. Well, Warner is the first scientist who successfully studied coordination compounds. He took cobalt chloride and he reacted it with NH3. After reaction, he got cobalt chloride .6NH3. Secondly, he added silver nitrate to cobalt .6NH3. After reaction, he got 3 moles of AgCl3 are silver chloride in the form of white precipitate or white PPT. Now listen carefully. Warner Baba thought that 3-chlorine are weakly or indirectly bonded to cobalt and 6NH3 is strongly or directly bonded to cobalt. That's why chlorine loved to react with silver. So he rearranged this compound. He writes the central metal atom of cobalt, then he takes NH3 and there are 6 molecules of NH3. He puts square bracket around these two species. Finally, he writes chlorine and there are 3 of them. So Warner Baba therefore said that 6NH3 are directly bonded to cobalt and 3-chlorine are indirectly bonded to cobalt. He called this compound as coordination compound. Remember that this is the first coordination compound in chemistry. Now what is the conclusion of Warner's theory? Well, Warner Baba states that every metal atom of coordination compounds has 2 types of valencies, primary valency and secondary valency. Primary valency is satisfied by negative ion. For example, here in this coordination compound, chlorine is a negative ion. It satisfies the primary valency of cobalt, while secondary valency is satisfied by positive ion or neutral molecule. For example, here in this compound, the NH3 is a neutral molecule. It satisfies the secondary valency of cobalt. Secondly, primary valency represents the oxidation state of a central metal atom, while secondary valency represents the coordination number. Thirdly, primary valency is denoted by dots and secondary valency is denoted by line. Fourthly, primary valency is ionizable. For example, chlorine is ionizable in aqueous solution, while secondary valency is not ionizable. For example, NH3 is directly bonded to cobalt. It is not ionized. Thus noted down all these important points. Now how can we calculate primary and secondary valencies of a central metal atom? Well, consider these coordination compounds. We have already learned that primary valency is the oxidation number of a central atom and secondary valency is coordination number. Now in case of this molecule, the central atom is cobalt. I am going to find its oxidation state. I write cobalt plus 6 into NH3 plus 3-chlorine equals 0. We know that NH3 is a neutral molecule, so its oxidation state is 0 and that of chlorine is positive 1. So I write cobalt plus 6 into 0 plus 3 into negative 1 equals 0. After calculation, I get positive 3. The oxidation state of cobalt is positive 3. So the primary valency of cobalt is 3. Here we can see that there are 6 ligands of NH3. So the secondary valency of cobalt is 6. Secondly, in case of this molecule, I find the oxidation state of iron. I write iron plus 6 into Cn equals negative 4 because the overall charge on this coordination compound is negative 4. We know that the oxidation state of Cn is negative 1. I write iron plus 6 into negative 1 equals negative 4. After calculation, I get positive 2. The oxidation state of iron is positive 2. So the primary valency of iron is positive 2. Here, there are 6 ligands of Cn. The coordination number is 6. So the secondary valency of iron is 6. Therefore, using this trick, we can easily calculate the primary and secondary valencies of a central metal atom. Now let me teach you the structure.